Next speaker is Max Schwick from Lisbon. And on the program, he's talking about TBA, but apparently that's to be announced.
Hello, I'm Max, and I'm going to talk about semiclassical decoding of resonant transseries. Can you all hear me well if I talk like this? Or great. So let me start by thanking the organizers for the opportunity to speak here, and also for the Newton Institute as our gracious hosts. And yeah, that's my topic. And this will mainly concern work that is about these two papers. One of them is with my fellow PhD students, Salvatore Baldino and Roberto Vega, who's also in the audience, and my supervisor, Riccardo Schiappa. And the other one is about with Riccardo Schiappa and Marco Marinho, but it's not published yet. Yeah, let me start motivating a little bit what I'm going to do. So generically, well, as all people in the audience probably know, is that string theory is generally defined perturbatively, and so we have such a series that is asymptotic, and from this, well, we will get additional exponential contributions. And the thing is that, well, the instanton contributions with a minus in front of them, they are very well studied, very well understood, but there seem to be what we would call the resonant brothers, basically contributions that have, well, a plus in front of them, and they actually produce a lot of hassle, and most of my talk will concern itself with these contributions and understanding better these contributions. For this, we basically consider two playgrounds. Well, one, minimal strings, and there we will just focus on basically the minimal strings with simple charge equals 0, so which are connected to the Painlevé I equation, and then Hermitian matrix models, and these will also be the two parts of my talk. So in the beginning, I will talk a little bit about Painlevé I basically, and then I will talk about Hermitian matrix models. So perhaps let's start a little bit, just Painlevé I, so famous Painlevé I equation, yes, so the specific heat of C equals 0 minimal strings fulfills Painlevé I. And from there, we could calculate the free energy by double integration, and from there, partition function, and we would be very well in our string theory. But here, so the Resurgent Resonant Transseries has been written down a long time ago, 2-parameter. And the hard question that we will try to answer is basically Stokes data. So I've shown here a little bit the grid of Stokes data that we will concern ourselves with, and I will be more specific soon. And the second part will concern itself with Hermitian matrix models. So I've given here just the matrix integral. And in the large n limit, in one-cut case, these Hermitian matrix models are described by a one-cut spectral curve. Well, these matrix integrals, they are also related to Painlevé I by double scaling, as probably all of you know. And well, here we will ask the question, can we give a full semiclassical decoding for Hermitian matrix models? So what do we mean by this? For this, we mean that on the one side, we have a resurgent transseries. On the other side, we have a matrix integral. And the question is, can we really relate each term in the resurgent transseries to a specific matrix integral? Okay. And it will turn out that this, if we do this properly, it will allow us actually to analytically compute Stokes data for Hermitian matrix models. And by this, I mean more than just the trivial Stokes, so the well-known Stokes that has been known for a long time. And moreover, we can give a physical meaning to the transseries itself. Okay. So, well, that's the structure of my talk. First, basically, I'm going to tell two stories. The first story is Painlevé I Stokes data, and is related to the first paper I mentioned. The second story, semiclassical decoding of Hermitian matrix models. Okay. So let's get started. Well, so what are we interested in? Well, I had already said the Resurgent Resonant Transseries has been established a long time ago. And what we are really interested in is Stokes data. So we want to understand, well, we have the an asymptotic region 1, asymptotic region 2, and we cross the Stokes line with an automorphism, and this automorphism will be determined by Stokes data, and we want to really understand what's happening there. So let's introduce some, or just very quickly go over just some namings just so we're clear. So we have a series, and I didn't put any convergence condition or anything. So it's basically a collection of numbers, an odd collection of numbers. We have a given one transseries, so we have factorial growth basically, and we can improve convergence of a divergent series. We can go to a convergent one using a Borel transform. I mean, this is all known. I just want to establish the symbols because I'm going to use them soon. Second part, once we have our transseries, how can we actually move from one asymptotic region to another? Well, we can use the Stokes automorphism, and it can be written in terms of, well, what's called the pointed alien derivative. This is very much, and the alien derivative is related to those Stokes vectors. And our goal will basically be to identify those Stokes vectors. So, because if we know those, we know how this guy acts, and we know how to cross Stokes lines, and we're happy. Okay, there's another way of writing the Stokes automorphism, which is basically in terms of Borel residues. This is just another way to encode Stokes data, and it's a very useful one because it's somehow more direct. So most of the times when you calculate Stokes data, you're actually calculating the Borel residue, and then you have to do some combinatorics to go back to your Stokes vectors. So those two sets exist, and we will want to find out this one, but most of the time one calculates this one. Okay, so let's get started. Painlevé I transseries. So I had already mentioned the Painlevé I equation. Perturbatively, it has such an expansion with a 2g factorial growth. And it's a second order differential equation. We have two instantron actions, and those instantron actions come in pairs, right, with a plus minus sign in French derivative, which we would call resonance. In other words, if we were to look at the Borel plane of this problem, we have singularities that are not just attached to one sector, but to multiple sectors of the transseries. Okay, and we will be very much concerned with those signs later on. Okay, so the full two-parameter resonant transseries solution that has been known, and okay, it contains logs in the sectors, and we already had a discussion on if logs are related to resonance or not, but for us they very much appear. So I'm not going to further comment on this. And each sector is a divergent transseries, and moreover, the log sectors, they are actually not independent, and this well, I'm not going to use this a lot, but it's a useful thing to keep in mind that the logs do not really change our game. Okay. We want to cross Stokes lines, as I had said before, and because we have a positive and a negative instantron action, we have also two Stokes lines, one across the positive real line, one across the negative real line. And well, we would call it the forward Stokes automorphism, which crosses 0, and we would call it the backward Stokes automorphism that crosses pi. And we want to be a little more explicit about those automorphisms, so we can ask, how do they explicitly act on the transseries? And if we do this, so I have here shown a grid of transseries sectors, so it would be the perturbative guy, one instantron guy, two instantron guy, and so on. And we can ask, what does an automorphism do when I act on a sector? And we could, for example, start at the 0, 1 guy and undergo a forward Stokes transition. The arrows that I've drawn here are Borel residues. And we can see, because of our resonance setup, because it's a very complicated transseries, we have a lot of arrows. So, but if we want to know all of Stokes data, we have to be very explicit about exactly those arrows. Okay. Well, now that I've talked a lot about Borel residues and Stokes vectors, let me be a little bit more explicit about the two sets. Oh, I'm sorry. Let me be a little bit more explicit about the two sets. So we can relate one of them to the other. And I don't know why there it is. And they are related by such a relation where P basically just contains products of Stokes vectors. But the important part here is that if you look at the two sets, Borel residues are indexed basically by two sets of numbers, an M and the second ones, whereas Stokes data just has two entries. So the set of Stokes data is much smaller than the set of Borel residues. So in a sense, if we want to know all of Stokes data, we don't have to know all Borel residues. We have to know a minimal set. So let's start to identify the minimal set. Well, and it turns out that it's actually good practice to know all of the Borel residues that start at diagonal sectors and go to any other sector. If we know those, we know the whole set of Stokes data, and from there we could produce all the other Borel residues. So this is, let's say, the first simplification that we can make in our calculation. Then let's actually concern ourselves with the set of Stokes data, and it has this structure. So it's conveniently arranged on a grid, and the grid basically ends at 1 in both directions, but it goes to -infinity in both directions too. And the reason that we have so many of them is just because we have the full 2-parameter resonant transseries, right? Very often for Painlevé one just sees the first guy, and the first guy would be this one. But we have much more of them. Furthermore, because of the specific structure of our transseries, we can establish something that we call backward-forward relation, which relates the forward Stokes data to the backward ones. Why do I say forward Stokes data? Well, because the lower triangle is related to the forward Stokes automorphism, while the backwards triangle is related to the backwards Stokes automorphism. And given that relation, it's sufficient that we just focus on one of them because we get the other for free. So from now on, just this triangle is interesting. Furthermore, I had mentioned that Stokes vectors are actually vectors. So they have what we would call a vector structure, namely there's a beautiful pattern that the vectors make that is, yeah, well, easily seeable, right? 1, 0, 2, -1, 3, -2, and so on. So we can reduce the problem even more because we don't have to know all the entries of the vectors. We just have to know the prefactor, really. So we are really just interested in the ends. So now we have already established a lot of structure on Stokes data that basically just comes from the transseries structure itself. We can move on to really calculate these guys. And to do this is, well, is a hard problem, but I just want to give a very basic philosophy. So on the Borel plane, we would have what we would call a simple resurgent relation. And here I'm showing just an example one where we don't really have a function here. We just have basically a pole. We have just a pole that's attached to, let's say, the 0th order guy of a would-be function. So the structure on the Borel plane is just very easy. I'm just putting an example to understand better what's happening. So if we had such a construction and we say we just have the singularity at A, this guy is somehow a series that has convergence radius A. If we were, this series converges really in the circle, and if we were to walk closely to our singularity, we could say what we mean, what this Borel residue is. So in a sense, if we just manipulate this, we can basically get something that we would call an asymptotic relation, which just means that this is a relation that for large K holds, and this K should have the color red.
Can I ask you a very simple question? I'm not in the field. So generically, depending on how you take the Borel sum, whether you divide by gamma, the singularity might change. So yes, this is a residue for a simple Borel.
Yes, so Borel. Exactly, this is a specific Borel, and the statement.
The standard Borel comes automatically to do the job.
So the statement is somehow that if you start with a series that is Gavray-1, there is a Borel transform, so you have to choose a good Borel transform that gives you a simple resurgent structure, by which we would mean that on the Borel plane you find poles and logs. And here I've just to simplify everything because I just wanted to give the philosophy. And then everything, yes, yes, every time. And here I just killed the logs just because I wanted to be pedagogic. I tried to be pedagogical, yes. So, so having such an asymptotic relation, we can kind of clean everything that we know to the one side and then isolate the Borel residue. And well, now we would just have to take the large K limit here in this sequence, and we would find the Borel residue. You can imagine that this procedure is, of course, incredibly inefficient because we're basically trying to evaluate a series. So one has to, if one really wants to calculate Borel residues, one has to be much smarter about it. But I'm not going to go into details, but there's a lot of numerics that can hide behind this, and this is very complicated. I just wanted to give the general philosophy that on the Borel plane, you want to basically understand your singularities. If you understand the singularities, you're good. So that's the idea. And going through this, we can find numerical approximations of those Borel residues. So far, so then our calculations from here are numerical, but we will use the numerics to then try to conjecture generating functions for Stokes numbers that we can then check. So we are now going through a short numerical step, but then we hope to go back to full analytics and then check the analytics. Okay. So, well, if we just calculate a lot of these guys, and I had already said we reduced the problem of calculating Stokes data to calculating those ends, we can find patterns between the ends. And I mean, those patterns are quite crazy and they contain crazy numbers. So they contain zeta numbers. And these patterns continue, of course, and they're quite insane. And to find them was great pain. Well, you can find them. And from here, you can kind of start guessing a little bit the structure that those numbers should have. And then this alone doesn't really do. What you can do is you can basically play the game of asymptotic relations that I had mentioned earlier. And what you can do is, so the asymptotic relations for Painlevé are much more complicated than the example that I had been looking at. And they contain, for example, these polynomials. They might ring a bell. They are Bell polynomials. And they have digamma functions in them. So they are very complicated beasts. But if we manipulate those asymptotic relations in a smart way, we can kind of reduce the problem to calculating what we would call these Ds. And it turns out that if you do this in a nice way, and you just do numerics, you calculate these guys numerically, you plug them in here, then these Ds are almost always 0. So then we can just conjecture them to be 0 in general and just use such a relation to calculate well, all Stokes vectors, or all the ends basically. And there's one thing that I would like to mention, that well, almost all of the Ds are 0, but we need 2 numbers to input, and it's basically the first numbers in the diagonals. So what do I mean by this? Well, let's go back to our grid of vectors that I had shown earlier. And here we have so we have these arrows, and the equation that I've shown here, this equation, is basically dictating us on how to walk along these diagonals. And the thing is that in each diagonal, we need to know the first 2 guys to determine the rest of the diagonal. But it turns out that, well, these 2 guys, they are kind of gettable. I had already said this guy is a known guy. And for example, this guy can be guessed, and it is this amazing number here. And well, I would already point your attention to the fact that it contains no Euler gamma number. We will revisit this later because we can actually do proper analytics from the matrix model side, and we will revisit those numbers. But the fact here is that we can calculate those diagonals, or we can conjecture all those diagonals. Well, and then we find generating functions for these ends that look like this. And here the guys in purple, they are the ones that you need to know in the beginning to conjecture the whole diagonal. As I said, there are 2 numbers missing, and here these are those 2 numbers. But the point is that from these generating functions, you can calculate all of the ends. And well, these are the numbers that we need to know. And here, for your convenience, I've just repeated the vector structure just to remind you. And well, we can, I'm sorry, once we have those guys, we in principle know everything about our Stokes automorphism. So we can really just undergo Stokes transitions, and we could try to do checks on our conjecture. So one check, for example, would be that Painlevé I, the solution to Painlevé I should be a metamorphic function. And somehow that means that the automorphisms should close at some point. Like, we cannot walk around arbitrarily many times. We should at some point go back to what we had before. So we can try to check this, for example, and one can do this. Or one could do isomonodromy checks, and Roberto Vega will talk about them later. And there's a lot in the literature about those checks. But here we will take a different path. We will now concern ourselves with the matrix calculation. So this brings me to the second part of the talk. And I'm sorry, I just want to check what my timing is. This brings me to the second part of the talk. And I will tell this talk, basically, I will tell this part in 2 acts. So the first act, I will basically review known things and just put them in a little bit different language. And as in any good play, at the end of the second act, we will have somewhat of a crisis of meaning, because we will see that actually our description doesn't, or the description that is established doesn't completely do to describe everything. And then in the second act, we will try to resolve this conundrum. So as I had already said before, this act is going to, or this part of the talk is going to be about semiclassical decoding of matrix models. And so what did we mean by this? Well, I said on the one side, we have a transseries. So this is very much the analog of the Painlevé Transseries, right? And it could even double scale for certain matrix models. We could even double scale to Painlevé I. So we have the transseries sectors, we have exponentials, and we have, well, the transseries parameters, the initial conditions. But there's already this feature in this transseries that it is resonant too, right? We have two actions that are, one has a minus sign in comparison to the other one. Well, so on the one side we have the transseries, and on the other side we have matrix integrals. And those matrix integrals here I've already written in a diagonal. I have written a diagonal version of this. What do I mean? In the very beginning, I had shown you an integral that was very much an integral over a matrix. Here I have already reduced this integral to an integral over eigenvalues, well, where we have used the unitary matrix to diagonalize, and we paid a price for it, which is the van der Waals determinant. But okay, so, and also please note the coloring. So the idea is that somehow we want to understand how the transseries sectors are related to integration contours of the matrix integrals. And this is what we will then call semiclassical decoding. And the idea is, how far can we go with this philosophy? Okay, so I've here repeated a little bit again what Act 1 is going to be about. So I'm going to review what is, well, the eigenvalue tunneling that's in the literature. Eigenvalue tunneling is just another word for fixing those contours in blue that I had shown you before. And then what's the relation? And then once we went through our crisis of meaning, well, we realized that actually we are missing something in the matrix integral. So the matrix integral, as I said before, is described by a spectral curve. The spectral curve has several sheets, and somehow it is standard to only consider one of the sheets. And our statement is somehow you should consider all of them. Well, and then we will do this. We will consider all of the sheets. We will get explicit expressions for matrix integrals. We will calculate them, and then we can compare with our transseries and see that we actually get the right things. And from here, we can also calculate Stokes data analytically. Okay, so let's not get ahead of ourselves. First, Act 1. Well, so this is our matrix integral already in diagonal formulation. We are very much interested in those guys. And this matrix integral is dominated by steepest descent contours, so Lefschetz symbols. And well, we can classify those steepest descent contours by saddle points of the potential. Here, because I will draw a lot of pictures of contours, I'm going to resort to the quartic example. And it's just, this is just because it gives beautiful contours. We could, in principle, have done any potential here. So let us now really draw contours here. And in the beginning, let's just choose a very simple case, namely the case where n equals 1. So then this matrix integral is really just an integral basically over the exponential of the potential. And we can draw steepest descent contours, and they look like this. So the steepest descent contours, they depend on the argument of GS, right? Because the condition of steepest descent here, it very much contains GS, right? So if I rotate the argument of GS here, my contours will change. And we can just draw those contours. So for example, let's start a little bit above the real line with the argument of GS and just rotate them. And then they will change like this. And the thing is that they change continuously until we pass 2 pi I or 4 pi I, 2 pi, I'm sorry, 2 pi or 4 pi, or also 0. It's just that I already started a little bit above the 0 line, above the positive real line. So these jumps are basically where the matrix integral undergoes a Stokes transition. And this manifests itself with the fact that, well, actually, if you wanted to continuously deform your contours, you wouldn't just jump here. What you would do is you would deform such a contour to this one plus a residual contour. And this contour, now I have here drawn the in red, I don't know if you can see this, the saddle points of the quartic potential that I had shown before. And while these contours are very much going through the perturbative saddle point at 0, these contours no longer do so. And this is what eigenvalue tunneling is, because somehow the new contours are dominated by non-perturbative saddle points, whereas the old contour were dominated by perturbative ones. And this is very well established in the literature, and I've also put in here the references. Well, but this means that the steepest descent very much sees the Stokes automorphism. So if we can do this, if we can perform the Stokes transitions with our steepest descent integrals, we could also perform them with our Transseries, and we can compare. So having established this for n equals 1, let's go a little bit more general. So, right, of course, n equals 1 doesn't do for us because we want to know it for all n. Second, we are at some point interested in double scaling, so we really want to take n to infinity. So, well, we can play the same game for higher n, and somehow for n equals 2, well, you have to do some combinatorics, and things become a little more complicated. But here I've already called things 1 instanton or 2 instance sector, just because, well, I know that here one eigenvalue has tunneled to a non-perturbative saddle. Here too, it's just that they are flipped. And here, both of them have tunneled to a non-perturbative saddle. And we can play this game in general. And here, so we would write something like this, where by this symbol, we mean that L eigenvalues have tunneled to non-perturbative saddles. And here, perhaps with the notation, you might already realize that something's missing because there's a 0 here that doesn't do anything for us right now. Okay, having established this, we can spell out both discontinuities once in the Resurgent language, which is this one. This is the well-known forward discontinuity starting from the perturbative sector in the Resurgent language. And on the other hand, we can calculate these zk0 symbols, and they are given by such integrals. And now I would like to state that, well, here we started with an integral, so one could assume that what we get out of here is really a function. But actually, well, how would you solve this integral? You would do well, your steepest descent methods and then do a saddle point approximation. And what comes out of the saddle point approximation is actually a divergent series. So actually, if we would compare this to this, we are comparing divergent series here. So we can match both. And well, matching both will look somewhat like this. We have the resurgent side, we have the integral side. Here, the resurgent relations get us two non-perturbative sectors. And here, the contour deformations get us two non-perturbative sectors. And we can kind of almost derive this relation because somehow this we can express as a discontinuity, this we can as a discontinuity, and we can just compare those discontinuities with each other and see, and then derive such relations, which are very much semiclassical decoding relations. And of course,
far, the Van der Monte determinant didn't play any role.
It didn't play any role yet, no.
At some point it will?
Yes, it will. But yes. So yes, I'm going to come to this. It's a little bit more. But so yeah, I have put this amazing picture of a bridge in Cambridge because yes. Okay, but having established this, we have done basically one thing. We have undergone a forward Stokes transition, and I have so far not talked about backward Stokes transitions at all. So what we can get from the picture that we have now is the forward guys. And if you compare this to the initial lattice that I had shown you, these are very few guys, right? Because there should be a whole lattice up here that we cannot reach. Why can we not reach it? Well, because if we remember the pictures that I had drawn for eigenvalue contours, they underwent a Stokes transition at 0, 2 pi, 4 pi, but they didn't do anything at pi. So the backward Stokes automorphism cannot be seen by these guys. So somehow we are missing well, you could argue half of the picture, but actually we are missing much, much more, right? Because we're missing the whole lattice that this half of the picture gives us. And this is what part 2 is about. And I'm sorry, I just have to check where I am. So this was perhaps I should have said this clearer. This was our crisis of meaning, that we had a good, we thought we had a good picture that then actually didn't pan out to give us the whole Transseries lattice, but just a little bit of it. So after having had this crisis, we want to try to resolve it. So to do this, let's take a step back and consider a little bit what we did here. So first of all, we were considering matrix integrals, and let's now really consider them in the large n limit. So in the large n limit, we are no longer just looking at the potential. We get corrections from the large n limit. Well, so our potential becomes an effective potential. I don't really want to be much more specific about it, but the point is that the effective potential basically is related to the spectral curve by derivation. So from now on, we can just look at spectral curves. So in the large n limit, those matrix integrals are basically expressed by their spectral curves. And this is, for example, a very common thing, right? In topological recursion, basically we give you a spectral curve, and you basically calculate the W correlators for me, which is a matrix model thing. So yes. So here I've drawn the cubic spectral curve, and how can we basically visualize eigenvalue tunneling on such a spectral curve? Well, this spectral curve has a cut, so it's a one-cut spectral curve. And the idea is that in the one-cut solution, all the eigenvalues sit in this one cut. So all the eigenvalues sit here. But then I had told you, when we underwent the forward Stokes transitions, one of the eigenvalues went to a non-perturbative saddle. And well, this was what eigenvalue tunneling was. So what would this be in this picture? In this picture, it means that one of the eigenvalues leaves the cut and moves here. And it does so along the blue path. But it doesn't do so somehow along a path here, right? I could have walked below, but I didn't. And so how would we, so what would be a simple calculation that we can do with this? Well, we can calculate, for example, the instanton action. And the instanton action is literally just, well, an integral over the path. I start here, I move here, an integral over the path on the spectral curve, and this would give me the instanton action. So somehow the big question that we have to ask, how can we get a minus here, right? Because I had said that a resonant transseries has an action and it has the same action with a minus sign. So what we would need is a situation where we produce a minus sign. And well, I think I was kind of suggestive that the spectral curve, well, it's basically, it has this square root here, right? So flipping sheets here will produce a minus sign. So yeah, so here I just want to outline again. So if we were to write out the free energy for the matrix model, we have a transseries that has exactly this structure. So it has resonant actions. And we are really just able to produce the n guy for now. And we would like to produce both in order to find basically all of the Stokes transitions that, for example, Painlevé had. Yes, but apart from this, this transseries is remarkably similar to the Painlevé one, which is very natural because somehow, for example, for the cubic or the quartic matrix model, we have to be able to double scale to Painlevé. So it's not surprising that, yeah, and such a transseries you could get from the string equation of the matrix model, right? Okay, so yeah, the big conclusion, standard eigenvalue tunneling is missing the second action. Okay, now how do we get the second action? And the idea would be, I had already said, to populate not just one sheet, but two sheets. So how do we do this? Well, actually, to be honest about it, we would have to basically go to uniformization variables of the spectral curve. And then it is very clear already that somehow you go to the sphere, and on the sphere you have 2 points, which somehow should be identified with each other, somehow the double points. And these points are the non-perturbative saddle, right? They are somehow what we would call the zero of the spectral curve somehow. So this point here. So if we go to uniformization, it's actually not that weird that we find two actions suddenly, even though we have just one saddle point, because the saddle point somehow on the sphere is split in two, as perhaps just as a picture. So we introduce uniformization variables and carry out the integration on the other sheet. In other words, we walk two paths. We walk the blue one and we walk the orange one. Okay, so let's do this. And to really do this, we have to understand in these uniformization variables how to switch sheet. And how to switch sheet is basically by just inverting. So you take a zeta to 1 over it. And we can see, so the actual variable x doesn't change, which is exactly what we wanted, where the spectral curve acquires a minus sign. And this is just due to the fact that the spectral curve had a square root cut. Okay, so now we can really do this. We can calculate the first action, and this is just what I had shown you in the previous slide. Basically, nothing happens. I've just rewritten it in uniformization variables. But I can calculate now also the second path. So this is basically calculating this path. I go walk from B to X star along the physical sheet. But now we could walk from A to X star along the non-physical sheet. And if we do this, we could rewrite everything on the physical sheet by doing changes of variables. And indeed, we could then compare our actions and we find a minus sign. Well, this minus sign is really just due to this minus sign of the spectral curve. So this means now we have our two actions. So having this, can we go further? Can we play the game that we played before? Now also with the, let's say, with our new eigenvalues, right? With the eigenvalues that now live on the other sheet of the spectral curve. And the thing is, yes, we can. Here, I've drawn the steepest descent contours for the eigenvalues on the other sheet. And this very much works exactly the same way as the eigenvalues on the physical sheet worked. It's just that now everything has a minus sign. So the fact that the spectral curve has a minus sign, what does this mean for the steepest descent contours? Well, this is somehow the same as just giving a minus sign to GS. In other words, we just rotate everything by pi. So somehow everything that eigenvalues do at 0, at the argument of GS equals 0, anti-eigenvalues do at the argument of GS equals pi. So this very much hints that we should find now a backwards automorphism just from eigenvalues on the non-physical sheet. So and indeed, so walking here, we again find the Stokes transition, but now it is going from pi minus to pi plus. And well, the transition looks pretty much exactly the same as it would look for eigenvalues on the physical sheet. So very much the steepest descent really now sees the pi automorphism. So having established this, let's really try to do computations with it. And to do computations with it, it's really not enough to just flip the sheet of the spectral curve. But before I had shown you a complicated integral formula with the determinants inside and everything. And if we were to say we want to go to the other sheet, we have to go to the other sheet everywhere. So now we have to know how to flip sheets of these determinants. And you can do this. So this is a formula that we have obtained by basically explicit calculation up to some GS orders. We have spelled this out explicitly, and we have just calculated that it gives this. And so this is a formula that is we don't know if it holds to all orders. It would be nice to see if it holds to all orders, but in GS. But so the orders that we are using, we calculated, and there it works. But it would be nice to prove that this is actually in general true. So in the way, this is a conjecture that we have checked. But anyways, so flipping sheets here, what does it do? Flipping sheets here flips the determinant. So this is good. Somehow our integral changes, which is good because we need to find something different if we walk along the different directions. But there's another very interesting thing that happens everywhere where before we had a -1. So basically this -1, where does it come from? It comes from the fact that we took an eigenvalue out of the cut and moved it to a non-perturbative saddle. But that means now there's an eigenvalue less in the cut. So everything will have a -1. But interestingly, this changes. We find instead of a -1 after flipping sheets, we find a +1. And this +1 gives somehow an interpretation of what eigenvalues on the other sheet are, because they are somehow like holes on the physical sheet. So if we were to take if we wanted to move an eigenvalue, what we would have to do is in the cut, we would have to produce somehow an eigenvalue hole pair. Then we would move the hole. And then because there we produced an eigenvalue, suddenly there's an eigenvalue more in the cut than there was before. So, well, yeah. So on the involuted sheets, we will now start calling those involuted sheet eigenvalues we will denote them by anti-eigenvalues. So the philosophy is always we take anti-eigenvalues and we want to tunnel them on the non-physical sheet. But in order to make the calculation easier, we will of course rewrite everything on the physical sheet. And on the physical sheet, we will call these new eigenvalues anti-eigenvalues. Okay. So having done this, we can really repeat our calculation. And for example, I had shown you already. This is somehow the one instanton sector that we got just from undergoing the forward Stokes automorphism. But now we can undergo the backward Stokes automorphism, and we find the 0,1 instanton sector. And it looks like this. And one can do this integral. And well, should find the Stokes constant in the backwards direction and everything. So then we can, of course, also again do our matching of Transseries guys with matrix integral guys, and the matching works again. So in the sense we have a very direct interpretation of what we mean by of what these guys have to be for the Transseries. And here you can see, so this is the result of this matching. You can see that the backwards guys in the Transseries are indeed given by this type of integrals. So here I've just written it for 1 to make a very direct comparison here that you can see what changes. So what changes here, the n-1 becomes an n+1. Somehow the contour changes because it's rotated by pi, as I had said before. And the determinant becomes 1 over the determinant. And there's a minus sign that changes here, right? This is from the formula that I had shown you before. Okay, having established this, can we do this for the more complicated guys of really tunneling k anti-eigenvalues? In other words, can we produce the 0k instanton guys? And the answer is yes, very much. The formulae I have exactly the same spirit as before. They're just a little more complicated. So we again X bar our anti-eigenvalues. We have 1 over the determinants, but now we have a product because we have multiple of them. And we have now, because we have tunneled k bar anti-eigenvalues away, we have to add k anti-eigenvalues to our cut. So everything is the same. The picture is just a little more general. And again, the bridge relation is the same as I had showed before. Okay. Now, let's draw a picture about this. And this is just somehow summarizing what I had said before. So the blue side is somehow the side that was known. If we undergo a forward Stokes transition, we tunnel an eigenvalue, and the eigenvalue leaves the cut, so there's one guy less here. Backwards, if we undergo the backwards Stokes automorphism, well, an anti-eigenvalue leaves the cut, so somehow it moves to the non-physical sheet. But as we said, if we write everything on the physical sheet, we basically have a hole. So a new guy appears in the cut. Well, yes, and perhaps it's important to notice that similar pictures have been drawn 10 years ago, but it wasn't very clear what the interpretation of these guys would be, or how to actually do those calculations. But in principle, there has been talk about this. Okay, and in this spirit, let me also add that the integrals that we are finding, they are very similar to what one can call supermatrix integrals. So there's this object, the physical supermatrix model, that looks like this. That's somehow very similar to the Hermitian one. It's just that where the Hermitian one just has these terms, the physical supermatrix model has also these terms, which are basically the same as the Hermitian ones, just with a minus in front of them. So somehow it's very natural that this is related to what we are doing, because we are also finding minus signs. Yeah, so there has been a proposal for these integrals also around 10 years ago. But yeah, it's probably fair to say that to really perform this calculations has not, yeah, this is what we've done. Okay, so after having mentioned this, let me move on to an even more complicated example. So for now, what we had was, we had somehow the full forward guys and the full backwards guys in the Transseries. But what we would be really interested in is some guy in the middle, right? So we would like to walk somewhere, let's say, to the L0 sector, and then undergo a backward Stokes transition, because that would somehow catapult us inside the lattice. And doing this, something new happens. This is the resurgent relation that just comes from, like, this is really just the resurgent calculation. What happens if you start at the L0 sector and you walk inside the lattice? What you find is a resonant sum of sectors and not just one sector. And this is due to resonance, and I think has been very well established. But the fact is that here sum appears. But this is not true for the matrix, for the tunneling of anti-eigenvalues. There we still just have one guy. So somehow what appears in our new bridge relations, I'm calling them bridge relations because they somehow relate resurgent stuff to eigenvalue, to changing of eigenvalue contours. So they are not bridge equations, but they are somehow giving a relation between these calculations. They contain now a sum, these relations. Well, they contain just the resonant sum from resurgence. And on the other side, we just have, well, what we would expect. A guy where L eigenvalue is tunneled and K bar anti-eigenvalue is tunneled. Okay, now let me just check how much time I have. I see. Okay, so we can draw again the same picture that we had before. It's just that now, so we find a resonant sum in the resurgent lattice. So for example, for the L0 guy, we find that we end up at these two guys. These are the resonant lines. Well, and then here I've drawn the effective potentials, and is exactly the same picture that we had before, just upgraded to the new situation. Okay, so now let's get to actual calculations. When we do this, we find some complicated matrix integrals, and they're a little more complicated than the standard matrix integrals that we had before. So we still have an integrals over determinants, but in addition, we acquire poles. And this is somehow due to the appearance, this is somehow due to the Vandermonde determinant that will spawn, spawn those poles for us. And the fact that these poles are there means that our contour deformations that I had shown you earlier don't just go through. Now, we pick up when we try to deform our contours from perturbative ones, because with perturbative contours because of Stokes line, then we deform them to non-perturbative ones. Now we will pick up residue contributions that are due to these poles. So a deformation that before might look like this, now looks like this. And we suddenly have an additional closed contour that we have to take into account. And if we do this, we can just calculate these additional residue contributions, and they look like this. So I've given here an example calculation where it's literally just, so we take the residue contour, we have here the pole, and we pick up these guys, and we see that we get these extra terms. And they actually appear in the Transseries. Okay, so what did we calculate with this? Well, what we calculated are, well, these sectors. So we calculated forward guys, purely backward guys, but we also calculated the 1-1 sector and the 2-1 sector. In principle, we think we can just go somewhere inside the lattice. It's just that these calculations are really complicated and really long. So this is why we just calculated those guys. But the thing is that with these calculations, we also find Stokes data. So we can, of course, reproduce the known one. We can reproduce its resonant brother, but we can also produce these guys, which are completely new ones. So this is a 2-step Stokes constant and a Stokes vector somehow. And this is very much the non-trivial one that contains the Euler gamma number. And we can do these calculations. Let's start on the boundary. So the boundary, this is somehow the calculation that is known, but I would like to point out 2 things. First of all, it has a quadratic starting genus, which is true for the partition function of matrix model. Second of all, the result depends purely on the spectral curve. So all the red things that are written here are spectral curve data. So in a sense, if you give me a spectral curve, we can produce data. So backwards, it works in the same way. It's just that now with very slight differences. So there's a minus sign different. Okay. Then the 1-1 contribution is the same way. It is a very similar calculation. And here I would like to point out 2 things again. One is that we are not restricted to the first order. So this is some of the contribution that I had already shown you. This is the residue contribution. But in principle, we can go to any GS order with a lot of pain. But one could, because it's a saddle point calculation. So it's a very complicated thing. And the other thing is that what we're actually computing here is a ratio of partition functions. Like everywhere, we have computed ratios of partition functions. So the real objects that we are studying are somehow free energies. It's just to be very, very clear about this. Okay, so having said this, let's say, the crown jewel of our calculation, which gives us, well, a lot of things. So this is somehow the calculation of the 2-1 sector. But keep in mind that this is the first one where a resonant contribution appears. So this doesn't just have the 2-1 sector, it also has the 1-0-1. And the one that is interesting, the thing that comes attached to interesting data is actually the 1-0-1, because it comes attached to logarithmic contributions in the transseries, this guys, and it comes attached to a new Stokes constant, a Stokes vector, this new Borel residue. This is the guy that contains the Euler gamma number. So, and you can already see that in the final formula of the calculation, the Euler gamma number appears here. So we can do this. And now, having established all these formulae, let's philosophize how more general Stokes data can come from. Well, somehow the old analysis was somehow, okay, we have a generating function for Stokes data, and it is a 1 over gamma function. And if we expand it, we get all the guys. We get the Euler gamma number, we get the zeta. So this is somehow zeta 2, this is zeta 3, and so on. In our new picture for matrix integrals, we would get those numbers from a very different consideration. We would get them from such integrals. So we get it somehow from well, yeah, such integrals appear naturally in our calculations, and this is how these numbers would appear. So, well, this is just a side comment on the transcendentality of Stokes data, because somehow we would have to produce all of those, right? So there's another side comment that I want to make, and I want to make it very quick. I had promised not just the non-trivial Stokes vector across the first diagonal. I had promised this 2-step Stokes guy, and it actually just comes out of our considerations by basically consistency of the matrix integrals, that depending on how you walk along the transseries lattice, you can produce slightly different matrix integrals that have to coincide somehow. And just asking for consistency produces a 2-step Stokes vector out of 1-step guys. Okay, now we can actually check this and do examples. So for example, the cubic and the quartic matrix model are incredibly well known. So we could just take our 1-cut spectral curves, plug them in, and see what we get. And compare, for example, with the results that we get from expanding a string equation, right? We take the string equation, we plug in our transseries ansatz, we calculate everything, we calculate large order, and we see what we get. The answer is, so first of all, for the transseries sectors, we find perfect agreement. But moreover, we can analytically calculate Stokes data. And well, these are the ones that we calculated, and we can already see that this guy is kind of akin to Painlevé I, right? We have a Euler gamma number, we have this 96 square root of 3 that also appeared for Painlevé I. And that's not natural, because the cubic has to be able to double scale to Painlevé I. Well, in the same way the quartic works, it's a different spectral curve, well, coming from a different potential, but again, same story. We have perfect agreement between our calculations and results from string equations, and moreover, we have analytical Stokes data, which is this one. Okay, then let's just finish by quickly laying out that we can actually double scale all of this, and then we have the analytic results for Painlevé I Stokes data. And so I'm not going to give more details here, but well, this is what we would get when we double scale our results from the quartic and the cubic. First of all, they coincide and give the same number, which is good. And second of all, well, this is really Painlevé Stokes data. Okay. Having established this, let me finish by concluding first. So the first part of my talk was about, well, conjecturing Stokes data for Painlevé I. And we had done so, we had found generating functions and so on. And the second part was about actually analytical calculations for matrix models here. And I would also like to stretch that the calculations that we have done here are not specific to one matrix model, or so, like not to a specific matrix model, in the sense that we can put in any spectral curve that's a one-cut spectral curve. So in that sense, all the results that we have there are universal. It would predict that for any matrix model, for any spectral curve that we plug in here, the non-trivial Stokes constant that Stokes vector that I had calculated contains an Euler gamma number, or that then all the zeta number structure should go through for all Hermitian matrix models and so on. So these results are actually, they concern very much general statements about Hermitian matrix models. Yes. So so that's somehow this point. And in this sense, we have also the full semiclassical decoding, because we can say for any guy in the Transseries what it corresponds to as a matrix integral. Okay, then, well, if we have this, shouldn't we be able to go further and tell you exactly what the non-perturbative partition function is like, right? Because in a sense, I told you, okay, I somehow know everything about the Hermitian matrix model, right? So we should be able to answer this somehow. But there are, of course, many practical problems involved here that we can't really answer. So, but in a sense, this would be a natural thing to ask. Then, well, can we do this also directly in the minimal string, right? So I had somehow said we have a full semiclassical decoding for matrix models, and I had said, okay, we conjectured things for Painlevé I, but Painlevé I is minimal string theory, so we should be able to do some CFT calculation that does exactly what we did for the matrix models. Okay, and then, well, somehow what we have written is only dependent on the spectral curve, right? This is somehow a similar story to what topological recursion is, right? It is also just dependent on a spectral curve, but it turned out to be much more general. So in a sense, given that everything we write here is also just dependent on a spectral curve, perhaps it's also more general than just matrix models. I mean, this is purely conjectural. I'm not claiming anything here, right? I'm just to to not yes. So yeah. Thank you for your attention. And
thank you very much for a very interesting talk. In the quartic case,
yes,
the matrix model has two things that you can vary, right? Inside the integral, there's the x and also then the size of the matrices. So there, yes. I think of it as two different variables. And the string equation comes from varying the n, the size of the matrix, while if you were to look at only the x variation, you would get the fourth Painlevé equation.
Okay. Yeah.
And the fourth Painlevé equation has its own Stokes structure.
I see.
So if you're doing the matrix model analysis without varying the size of the matrices for some fixed size ensemble, then I imagine that what you're seeing is also involving the Stokes structure from the fourth Painlevé equation. And so my question is, were there elements of the Stokes data that you calculated which disappear in the double scaling limit to the first Painlevé equation? Because they will be things that belong to the fourth Painlevé, but don't appear in the first Painlevé.
I see. So, so I think I have to make one comment before that. So the calculations where we calculate Stokes data, they're very much in the large n limit. So somehow we.
I see. I didn't catch that.
Yeah, perhaps I didn't make it very clear. Sorry, I should have perhaps made that clearer. Yes. So I don't think that, but in principle, we should be able to repeat similar things for finite n, but it's much harder because we don't really have the spectral curve picture, right? Where we somehow we got the spectral curve picture from going to large n, and then we had our two sheets.
I see.
And then we played our game.
Mm-hmm.
Yes.
This is a naive outsider's question. Much of what you said, these lattices, Stokes lattices that you reminded me of our hyperasymptotics in the 1990s, where in much simpler situations than yours, we found that if you repeatedly apply resurgence and Borel summation, you get, for example, where you have saddles, you start with one saddle and then repeatedly more and more saddles at each stage become visible and contribute. And some of what you said has a very strong aroma of that. So are you doing in this much more sophisticated context what we would have called in the 1960s, 90s, hyperasymptotics?
I don't think so, but I'm not sure I'm familiar enough to give a very informed answer.
You
With
describe different saddles becoming visible at each stage.
yes, but
and that's exactly what we found and calculated explicitly for.
I see, but
cases.
somehow, yeah, I don't think I can give a very informed
And
answer. I'm
getting
very sorry.
smaller and
Perhaps I should.
smaller exponentials at each stage.
Yes.
By the way.
Yes. No, I'm not. I just. Let's say it like this. I would like to give an informed answer, but unfortunately,
Thank you.
yeah. Thank you.
So the Painlevé I is related to wall crossing and then so-called Argyros-Douglas A2 theory, which has either 2 or 3 PK states. So do you see a change of the number of Stokes automorphisms depending on the parameters of the spectral curve? So what you call A and B there, for example. So if you change these, do you see that sometimes you have
so-
more or less Stokes automorphisms in your problem?
Well, the number of Stokes automorphisms for us would be very much associated to the number of non-perturbative saddles, right? If you were to give me a spectral curve that has, I don't know, 5 saddle points, then of course there would be a let's say a forward and a backward Stokes automorphism associated to each of those saddles. Somehow, I'm not sure if that answers your question.
Yeah, so I think specifically in the A2, it's there will be 2, and sometimes you have the combination of the 2, and sometimes not. So it's depending on the parameters of the underlying.
Yeah, you can. Yeah.
So you don't encounter this in the
No, I'm not. No, not really. So in the sense of if we just so somehow this A and B, they are somehow fixed for us, right? Like it's not that we can just change them however we want because they are somehow telling us what the cut of the one-cut spectral curve is. So for us, if we would start here, we would go to a large n limit, and we would get A and B as functions of t. In this sense, I don't see that we have the freedom to change it. Or
Yes,
perhaps I
so
misunderstood
you
a
can
little bit.
approach the problem more generally and study it over the moduli space.
Ah, yeah, I
of
don't
the
know.
underlying curve, and then you'll have different.
I see. Yeah, I'm sorry. I have no idea what happens there. Yeah, maybe. Yeah. Sorry.
Thank you.
Yeah. But this is interesting.
So I'm trying to grasp this concept of anti-eigenvalue tunneling. So say I were to start in a 2-cut background.
Yeah.
Is tunneling an anti-eigenvalue from left to right exactly the same as tunneling an eigenvalue from right to left, or is there some
Yeah,
subtle difference?
this is a very interesting question, and in general, it is not the same. But there are situations in which it can be the same. But this is something that we still have to work out a lot. So we are very much attached to, we have a cut and then we move things around. And if we were to populate another saddle point with more than finite guys, we are not completely sure what happens. That's the honest answer.
Yeah. So to ask the same thing maybe differently, if I go from a 1-cut solution to a 2-cut solution, should I keep track of if the eigenvalues go through the upper sheet or through the lower sheet?
Yes, in general, yes, very much. Yeah, but as I said, so yes, let's say yes. I'm going to say yes.
Yeah. Okay, thank you.
Thanks.
Thanks again. We start back at 11:30, right? Is that right?